Welcome to Breadboarding. This is video 21 in the NanoComp Breadboard Computer series. In the previous video, we upgraded the CPU to the 68B09 8MHz version and also the support chips as well. And in this video, we're going to be trying to connect a hard drive to the NanoComp via an IDE interface. When I first started to look at how to connect some form of drive to the NanoComp, I did consider 3.5-inch floppy drives. However, when you look into it, the floppy disk driver requires a lot more coordination of the motor, searching, seeking, various other things. So, in fact, IDE disk driver software will actually be quite a bit simpler. Then considered some of the hard drives from the early 1980s. So, early hard disks were of a type known as MFM or RLL, typically about 10 to 110 megabytes. These had really complicated controllers and are quite rare and unreliable these days. But if you have a look at Adrian's Digital Basement video here, which will be in the description below, he spends an hour or so trying to get a number of drives and controllers working, and also then actually takes one apart. And so this particular drive is a 5.25-inch hard drive, so you can see the disk platter there, and you can then see the drive heads here, the mechanism that moves the drive head over the disk, and the motor in fact down here which drives this head was the thing that actually failed in this particular one. So I recommend having a look at that video if you want to know more about the legacy hard disks. So then I was considering the hard drives from the 1980s, and I'm trying to go with 1980s, perhaps early 90s chips and components wherever possible in doing this project. Otherwise, I may as well just get a Raspberry Pi and run an emulator on it. And the original IDE ATA drives were introduced in 1986 with the Compaq Despro 386. And it is still possible to get IDE drives on eBay from about £20–30, but they're likely to be old and unreliable. I did have a number in the past and I disposed of them, which I regret now. So what I've decided to do is to go with a serial ATA modern drive with an IDE adapter. So I have a spare 500GB SATA drive, a 2.5-inch laptop drive. The advantage of these is they run off 5 volts. And I've also successfully been able to get success with working with a StarTech 40-pin IDE to SATA converter. I had tried a couple of other devices that I got from Amazon, but I haven't had any success with them yet, so I may do a subsequent video to see if I can get other IDE adapters working. So this is an extract from the original Compaq 386-25 design from 1988. The earlier versions of the Compaq documentation didn't actually have the IDE disk controller. It's known kind of in the Winchester subsystem, so early hard drives were known as Winchester disks due to the original IBM team developing I think the 3040 or 3030 IBM disks called them Winchester for one reason or another. Now, the IDE interface is actually very simple. So on the right hand side here, this is the 40-pin IDE interface. This actually interfaces to the PCAT ISA bus via 2 bidirectional buffers. There are a couple of other control logic chips and an additional buffer down here for buffering some address signals and some of the read and write control signals. But the actual IDE interface is particularly simple, and most of the complexity is actually built into the disk drive itself, hence integrated drive electronics disk drives. So I started to look for some example designs. So there are a couple of example designs for 8-bit micros, a Z80 and a 65021. And they're in the URLs below here, and I'll just show you quickly those sites. I'll include the URLs in the video description below. So 2 IDE interfaces, both support 16-bit to 8-bit conversion, so 8-bit bus to 16-bit IDE drive. This first one has good documentation and includes sort of a detailed design and schematic here. I did find that some of the control logic here was a little more complicated to work out what was going on, but it does also include quite a good example software in Z80 assembly language, which helps to explain how to access the drive and do all different things. And you'll see here there's actually neat procedures for getting the drive ID, which is the 512 bytes of drive identification information you can get out of the drive, and also how to read and write sectors. Then the second example, which was from Lee Davison's website, this actually had 4 chips used to actually access the IDE interface and 1 program or logic device to do all the control signals. Now this actually makes use of 2 buffer chips. In this particular case, they are the bidirectional 74LS245 chips. Now these are actually wired to only go in one direction. So in fact, I've replaced these with single direction buffers, the 74LS541. And then there's also 2 latches here, and the reason why these 2 latches are required is what this interface does is when we write the data to the port here, it makes use of the address A0 line to control between the lower byte and the upper byte. And what this arrangement does is latches the upper byte when reading it, and when writing to the drive, it latches the lower byte and then sends both bytes to the drive when the upper byte is actually being written. I'll explain about that when we look at the schematic. But it basically means that we can read and write 16-bit data to the drive and without really having to worry too much about it. This example includes documentation and also a sample basic program as well. So these 2 sites that I use for doing most of the documentation and the design for this particular project. So I'm going to be using Lee Davison's design, and the only thing I did find out on this is that because of the way how the 16-bit data is arranged, we need to write all 16 bits of data when writing to the registers in the IDE interface. So that was something I found out as I was developing this, that I can't just write a single byte to the low address. I actually need to write 16-bit data because it only gets latched on the writing of the upper byte. So in order to use the 2.5-inch SATA drive with this IDE interface adapter, trying to actually get an early version of DOS and the boot sector on this particular drive was quite difficult. One of the issues is that the early versions of FDisk and SYS and various other things like that will leave a disk alone if it detects that it has the 55AA disk signature on the first sector, so it won't do anything with that. Later versions of FDisk allowed you to overwrite it with the /mbr switch, which I think was in Windows 95 onwards. So trying to get a clean disk, it was quite tricky. In the end, I used a disk eraser software DBAN and then formatted with DOS 3.3 using a 16 megabyte partition with FAT12. I also found out that I could have done this a bit more easily. Windows 11 does include, and Windows 10 includes disk path. The only thing you have to be very careful of this is that disk 0 is normally the boot disk, but if you select the external disk, say disk 1, you can type clean to remove all the partitions and boot sectors. If you do clean all, it will actually zero out the whole disk as well. So that's probably an easier way of doing things. DBAN can take probably 5 or 6 hours to wipe a 500 gig drive. This is quite a bit quicker. Now, in order to test that I'm able to read data off the disk properly, what I thought I might make use of is the image that we used in the high color graphics videos, and that's the Doom sort of 256 color image. I already have an S-Record format of that, so this is the Motorola format of encoding binary data in a text format. And so what I was going to do is to copy the S-Record file onto the root folder of the drive and then see whether or not I can read that off it. And what I'll be showing you in a minute is using DOS 3.3 and an old laptop to be able to actually see which sectors that particular file is located on that hard disk. I'm just going to show you now, though, is, for those of you who may not be familiar, just show the different form factors of the drives. What I've got here is, this is a 5.25 inch CD DVD drive. Now, this particular drive, although it's the full width, this is a half height drive. So the majority of disk drives and CD drives in the last 20 odd years have been half height drives. The hard drive that was shown in the image from Wikipedia was actually a full height drive, so it would actually be twice the height of this particular disk here. This is a 3.5-inch drive, typically in desktops. This is a 500 meg drive and would be typical of modern hard disks in desktop PCs. And then this is the 2.5-inch SATA drive that I'll be using, and this is the StarTech IDE to SATA converter. So it has the SATA connector there that plugs into the drive there, and then on the other side we've got the 40-pin IDE connector, and it also comes with the necessary Molex power connectors as well. So I'm just going to show you how I've set up the 2.5-inch SATA disk drive that I'm going to be using with the IDE controller. Now this is plugged into an old AMD laptop which I've got access to. Now this does have Windows 10 installed on it. However, if when we go into the BIOS here, if we disable the UEFI BIOS support, then the way how this laptop's configured, it won't start up Windows 10. And we've also got legacy USB support enabled, so that means it should allow older legacy operating systems to boot off USB. So if we go in to have a look at the boot menu here, you can see that my external USB hard disk drive is actually first in the list here. We don't have an external floppy disk drive or a USB key, so those will take priority over the internal hard disk drive. So if we now just go into reboot, this will come up into MS-DOS 3.3. This is booting off the 2.5-inch disk drive that I'm going to be using. Now I'm not going to be able to run any of MS-DOS or anything like that because obviously we're running a 6809 computer. What I just wanted to be able to do is have a very simple disk where I could show the Doom S-record file, which we're going to use to test reading off the disk. So you can see here that I've got the DOS in a subfolder. I do have a few DOS configuration files, but I don't actually have the path defined, so I'm just going to set the path to CDOS. And what I'm going to do is just look at the first couple of lines of the Doom S-record file. So if we just look at this and we pipe this to more, so we can see here that the file begins with an S1 record type. 06 is the number of bytes of data contained in this row. Then we've got the address, which is 4000, and then there's actually 3 null bytes after that with the checksum on the end. Now, if we want to find this file in the sectors, raw sectors on the disk, we can search for S106, and that should find us the first sector of this particular file. So what I'm going to do is just to run up the disk editor. This is a free disk editor which is available in the URL, which I'll include in the description below. Now, hard drive 1 is not in fact the built-in drive, it's actually the external drive that I've booted off here. So I'm just going to select that drive, and this is the boot sector for this disk, and this is an old MS-DOS 3.3 boot sector. You can see there the messages and things in there which will be displayed if an invalid operating system is not available. We can't find a valid operating system. And you'll also see in the last 2 bytes of that boot sector there are the sort of magic numbers which are defined in a lot of PCs, and in this particular case 55AA identifies this as a valid boot sector. Now what we want to do here is also have a look to see what the definition of the partition table is. So we can see here down the bottom, don't worry about the bit at the top, there's a specific software that this disk editor was designed to work with Boot Wizard, which is not relevant here. So we've got a DOS FAT12 file system here which allows it a maximum of 16 megabytes, so this is actually compatible with DOS 2 as well, I believe. It's bootable, and obviously you can see here that it starts at cylinder 0, head 1, sector 1, all the way up to cylinder 1, head 254 and sector 63, and that gives us basically 32,000 odd sectors, which at 512 bytes each is about 16 megabytes. And we can also see down the bottom that the partition table signature is actually valid with AA55. Now what I'm going to do now is to search the disk to see which sector our Doom S-record file starts at. So we're going to be searching for S106, which you saw at the beginning of the file is the first line in the record, into hex. And what we can see here, we're on absolute sector 296, cylinder 0, head 33, sector 18. So that looks like it's the first sector. Let's just make a note of that whilst we're doing it to make sure we get everything right. That's 2096. Now we also need to find the last sector. Now I happen to know that the last record in an S record file is an S9 record. So if we now also search for S9, find S9903. That should find us there we go. So what you can see there is that our last absolute sector, which is 2440, and there's not very much in this sector. You can see here that basically we've just got the one line, which is the S903, 20 bytes, and then the checksum. And then after this, there's no more data in this particular file, so it's all zeros. So this sector is then just filled up with zeros. Now obviously if we read beyond the end of the file here, we're just going to be finding zeros. So we need to know what the length of the file is. So when we get to the last sector, we only read up to the end of the file and not the end of the sector. Okay, so we now know how many sectors our file is. We know where it is on the disk. So what we should be able to do then is use this to write the software to be able to read this S-record file and be able to load this into the video memory so we can show our Doom image. So I'm just going to have a quick look at the printouts of the technical documentation, particularly from the Compact S Pro. So this is the diagram that I showed earlier in the PowerPoint slide. The only thing I really wanted to show on this, we've got the IDE connector here, and there are a number of other signals that are actually coming out here. The key thing to note here is we've got pin 1 on the left hand side here. We've got the key on the even side, and this is important because early on when I was first developing this, I managed to somehow get the schematic diagram pin definition reversed, and it's also a little confusing in that this pin layout here is what the socket would look like, but in fact in the same document, so this is the pin layout that is included in the Compact document, but in fact we can see here that in fact pin 1 is on the left and pin 2 is on the right here, whereas this is reversed. So this is basically what the connector would look like, the end of the connector would look like, and this caused a certain amount of confusion when I was first developing this. So just be very careful whenever you're looking at diagrams, in particular the one on Wikipedia as well tends to show you what the cable looks like, not what the socket is. So I did have to do a bit of rework on this when I realised the error, and hopefully this will all work okay. What I have done on this diagram is actually annotated the pinout here with the signals from the example that I'm actually making use of. I'd also say that the Compact documentation is actually really the source for a lot of the standards for the ATA, IDE standards and things. And so you'll see here a lot of the signal names are actually the same signal names that appear in the standard. And in particular, one of the things which are a little confusing is that the drive select 0 and drive select 1 are known as CS1FX and CS3FX. And in fact, the reason for that is because these are on the I/O port 1F0 to 1F7 and 3F6 to 3F7. So this obviously refers to the actual I/O port that these things were originally located on, and explains why some of the standards and things use this terminology. This is the diagram from Lee Davison's project. I was just going to explain a little bit more about what was going on here. So again, on this one, the pin 1 on the socket is on the left here, pin 2 on the right. The key is on the right hand side here. So this is a view of the socket looking down on it. And what we've got here really is that the lower byte is controlled by these two chips up here, and we can see here that this is the IDE data 0 to 7. So these two sides are connected to the IDE drive data line 0 to 7, and then the middle bit here is connected to the CPU data bus. And then down the bottom here we have the disk drive D8 to D15 on the outside here, connected up here to the upper byte. So this is the lower byte, this is the upper byte, and the way how we switch between those is the A0 when it's 0 selects the lower byte, A0 when it's 1 selects the upper byte. One of the things you do have to also be careful of when writing the software for this is that a lot of the data is actual little endian rather than big endian. Now the 6800 series is big endian architecture and the Intel architecture is little endian, so it means we need to include the least significant byte first and the most significant byte second whenever we're writing word values. So that's a little bit of confusion. Now the programmable logic device here does address decoding. It also makes use of the A4 line is used to switch between drive 0 and drive 1, so chip select 0, chip select 1. Now at the moment I'm only using drive 0, so we're not really going to be really worrying about the second drive here, but that address line is used to switch between the two. The way how this works is that the buffer here, so this is a bidirectional buffer, but it's wired in one particular direction, so it's just wired in this direction. And so this buffer is used to actually read the data for the lower data from the disk drive and send it out onto the CPU bus. And so the signal here is low data read, but also when low data read goes low, it also latches the upper 8 bits of data from the drive into this latch, and then when we do upper data read, then the output enable on this makes that data available on here. So you can see here that when we access reading the lower byte, it reads directly from the IDE interface onto the CPU bus, but at the same time latches the higher 8 bits of data from the IDE drive into the latch, and then only makes those available on the address bus when we access the upper data read signal here. So that will be when the A0 signal is 1. And similarly, when we're writing data, when we actually write data to the IDE drive, to start with, when we do the lower byte, the CPU bus is latched actually into this latch here and doesn't actually go to the disk drive until we write the upper data. So we can see here that the clock signal for this is actually on the low data write, but the enable signal is only when we do the upper data write. And then we can see down here that when we have upper data write, then the value on the bus goes straight out to the IDE drive. So in this way, only when we write to the upper byte does the value that we wrote to the lower byte first go out here. So this does mean we need to write to the lower byte first and then the upper byte. Again, if we don't get that order right, then things will get messed up. So I'm using very much this design. There's a slight few differences between 6502, so the 02 signal there is the same as the 6809E clock signal. These select signals are just specific to the particular 6502 design. I'm going to be using one of the spare CRTC chip select lines that I have. And this GAL, I've used the design of this GAL as the basis for this and just modified it slightly for the 6809. So let's just have a look at the KiCad schematic. So this is the schematic diagram we ended up with at the end of the previous videos. This here is the keyboard controller chip, and we've got the sound generator chip and controller here. And all I've done is made this a little bit larger, and I've put the IDE controller design down here. So we have our 40-pin IDE connector here. Now we've got pin 1 on the left, pin 2 on the right, and we can see that the key is on the pin 20 here. And what I've also done is, just to make it a bit clearer, is I've identified that we've got the lower byte chips at the top here and the upper byte chips down here. So we can see here that we've got the CPU data bus common between the inner parts of these chips here, and then we've got the IDE bits 0 to 7 and 8 to 15 actually on these two ones. So there's quite a lot of pins here connected together. So all of these 4 sides of these chips, they're all attached to the data bus, and these two are connected together and then go off down to the connector here, and then these two are connected together and then go off down to the connector here. Then we've got the programmable logic device, the PLD here, that shall show you the rules used to generate those in a minute. And then this is used to actually drive all the various control signals. There are a number of these additional signals here that I have tied to ground or 5 volts on the basis of the sample projects and some of the documentation. When I was trying to get early versions of this working, I had a few problems, and these may or may not be still necessary, but I've left them in here just to make sure we don't have any problems. Then we've got the reset goes into the main active low reset signal from the main board, and then we just have the CRTC when we've got the CRTC Y3 signal, which is now identified as IDE. So there's basically a chip enable that we've got for this particular interface, and this interface will in fact has up to, I think, 16 or 32 registers that we can access via this memory map here. So let's just have a look at the files defined for the PLD here. So this is based on the example that Lee Davison provided on his website there. I've modified it slightly, so we're now using the CRTC Y6 line, which decodes to the D700 address range. And I've also changed some of the pins here where we didn't actually need the CPU E-clock, because the E-clock is already combined with this CRTC chip enable signal anyway. But much of the other signals are very similar, and this active intermediate term is used basically for controlling which address this is at, but this will just be based at D700. If we wanted to move it higher up that range, then we could change this particular term here. And then these values here show that chip select for drive 0 is when the A4 signal is 0. Chip select for 1 will be when A4 is 1. We're reading when A0 is 0, because this is the inverted value, and then we are writing when A0 equals 1, which is what I explained before, the way how the latches and things work. And again, these lower data read, lower data write, upper data read, upper data write are all defined in a similar way. Now, when I was doing this, I'd actually run out of the 574 latches. So what I have done here is I've made use of one of the another PLD here, and I've made my own 74LS574 latch. Now, the only issue is that the GAL here that is used can only have the clock on pin 1 and output enable is on pin 11, and that's the opposite way around to the normal 574 is. So I have done some chip labels for this, and this particular chip has the clock and output enable pins the opposite way around. I will order some more of these, but I'd run out of them since I'd used them all on the graphics card. So what this basically does is defines the pin 9 to 2 as D0 to D7, and then the D-type Q inputs are then defined as the D0 to D7. So this basically makes this a D-type latch, apart from these two pins are reversed. So I've printed out the relevant section of the schematic, which I'll be using to tick off as we build the project on the breadboard. And I needed a breadboard connector for the IDE connector. Now, originally I was hoping to be able to use a Raspberry Pi GPIO hat, a bit like this one. So it has the 40-pin connector here, and it also has the right sort of connectors to go into the breadboard. Unfortunately, when I looked at this in more detail, where there are voltage rails, so ground and 3.3 volts, all of these pins are wired together, unfortunately, so we can't actually address each individual pin separately. They're specific to the GPIO. So what I ended up doing is making my own adapter here. So this is basically just a bit of Veroboard strip board. We've actually got 4 rows of 20 pins. So what I have done is tested all of these to make sure that these pins are connected to each other and that the pins aren't bridged along the connection there. So that took a little while to solder and to test, but that means that this is actually should be hopefully fairly reliable. And I've also then put the chip label pinout is then included on here as well, so hopefully we'll avoid making too many many mistakes. So here's the breadboard layout. So I've put in a breadboard buddy for the power rails there, so that just means that don't have to worry about the power. I have actually got one of my breadboard power connectors made for this to plug into one of the power rails here. So this is the IDE connector. Now, what I know is that I need to have the upper data is here, so that's going to go to these 2 chips up here. So these 2 chips will be the upper ones, and so these 2 here. This is the PLD here, and then this is the lower, because the lower side of things needs to go underneath there. So what I'm going to be using here, I've got quite a lot of these DuPont cables where I've taken the individual leads off the end. So this is how these sort of cables normally come. They have these individual connectors like that. So what I've done is I've converted quite a lot of these to actually have these sort of 8-way blocks here, and that makes it much easier to actually plug in large numbers of address lines and data lines. So you'll see here that all these inputs here all need to be wired together, so this will make it a lot neater and easier to see. I'll probably put the cables in last because it's easier to actually see all of the other control signals before we put those cables in. So I'm going to put the connector up this end. There is a bit of space down the end here. May be able to possibly squeeze a floppy disk controller in there at some later point in time, but for the moment I'm just going to put the IDE drive connector here. So the key is here, and I've also put sort of white paint on the end there, so I can actually tell which side is 1. So generally with the IDE cables, then pin 1 is normally got the red stripe on it. And so what I've done here is I've made sure I'm getting my connections white around. This white there is where I actually drilled out the pin sort of block in there, just so that I could still use this sort of 40-way connector here without having to get rid of the pin there. So I could use it for other things in the future. So this cable will plug in basically like that, pin 1 at the end. So what I'm going to do now is I'll speed all the next wiring in as I tick off everything. So I'll speed that up and then I'll commentate over it. So just make sure the IDE socket's plugged in. Now just going to wire up all of the power rails for different chips. You'll notice that I've orientated the chips so it makes it easier to wire them up, not to have pin 1 all pointing the same direction. That's the reason why some of the power rails are slightly different. Once we put the power in there, tick that off the diagram, We'll also number the chips just so that I don't get confused when trying to connect things up. And they'll also put in some decoupling capacitors on all of the ground rails. Now we're going to put in the ground lines for the IDE connector, so there's quite a few ground connectors there. I should note that some of the camera angles indicate that some of these wires may not be going quite in the right place on the connector here, particularly on the top row, but I'll show a bit later when I tilt the connector up, you'll see that they are going in the correct one. Then there's a few pull up and pull down resistors that are in the diagram, and these were in the various documents and examples. Some may not be necessary, but in debugging the card I put most of these in, so I haven't tried taking any out. So then we're just putting in the activity LED, and you need to leave enough space for other wires to get around the corner there, so I just decided to move it over a little bit, so it just gives enough space for all the wires coming from the PLD to come up there. Okay, so now we're going to put the control lines into the first PLD. That's the LDR signal. So we're just going to wire in the LDR signal all the way up to that G2 enable. And then we're doing the other ones for the UDW and LDW for the other chip. Tick those off. So now we've got to do UDR and LDR for this other one. Wire those in, and then finally UDW for the other one. Now, in fact, on this one, it was easier to wire up the G2 and G1. I've swapped those around, so I've just updated the diagram. It's just easier to route the wiring there. Okay, so now we're going to take the drive or chip select CS0 and CS1 up to the relevant connectors up there. Now this is the cable I'm using for the address line, so it's split in 4 and 4, so we can do the 4 to 7 and A0 to 3 as separate cables. So now we're going to wire in the IA0 is going to A1, then IA1 is going to A2, and then IA2 is going to go to A3. Now the cable at the top there might look they're in the wrong hole, but it's just the camera angle, and in fact when we look at it another angle you'll see it's correct. Then we put in the IOW and IO right signals in there as well. Now we're just putting in the chip enable for the IDE and also the reset cables. Check all those off. Now we just really need to do the various data lines. So these areas here are all going to be wired together, all the data lines are wired together. We're going to need a cable then going off to the main data bus. So using these DuPont cables with the 8 sort of socket on the end. So just plugging the data ports on these 2 chips together and the data ports on the other 2 chips together. Then we need to connect those together. Slightly longer lead, making sure that the purple wire is normally pin 1 or 0, D0 for example. Then that is the data lead going off to the main bus. So that's where we're going to be putting in the output from the lower byte up to the top of the board there. And then we're just going to be wiring together all of the ID0 to ID7 and ID8 to ID15, wiring in the lower data lines there, then wiring in the upper data lines. You can see the pins are correct at the top there. Then just plug in the IDE connector. Okay, so we've finished laying out the board and I've ticked everything off, checked everything off. So this is our reset line. We also then have the CRTC IDE enable, and there's also the read-write signal as well that we need to plug into the main board. Then this lead from here is to the data bus, and then the other lead here goes to the A0 to A7. So all I need to do now is to test the main Nanocomp, make sure it's still working, and then we'll plug this board in. I've also put some of the chip labels on this connector at the end here. So we don't actually need to use this connector, but we can use this for putting logic probe in should we need to do any troubleshooting. So it's all done. Now let's fire up the Nanocomp, and then we'll have a look at the software that we need to test this and see if it works. So I've just powered up the main Nanocomp, and it's all working. We've got the prompt on the LED display. I've got the message on the video display as well. So it's all working at the moment. At the moment it's using about 1.3 amps at the moment, and I'll explain why that's important in a minute. So I'm just going to turn it off, and we're going to plug the board in. I'm going to put it up in this top area up here. I'm not going to plug in the hard drive for the moment. We just want to make sure everything works and doesn't draw too much current when we plug this in. So turn the power off. So here's our board. That's just going to operate standalone at the moment, and I've got made another power connector here, so we're just going to connect that power connector up to the corner there. At the moment I'm just going to leave the IDE cable free. Now we have a number of wires that we need to plug in, so this is the reset connection. So reset is over here, so I'm just going to plug this in next to another reset signal. We've got the data bus signals here, with purple is D0 going all the way up to D7 is black, so we just need to plug these in here. Okay, so now we need to do the address line. So again, this is A0 up to A7, and the address lines are down here. A0. Then finally we have read-write. So read-write is this one. This needs to go over here. So read-write is this one here. Then finally we've got the IDE chip select. Now that actually comes off the CRTC decoder, which is all the way down the bottom, just out of shot. So I'm just going to plug this into the CRTC 6 output. Right, so that's connected there, and I'm just going to put one of the voltage meters on here as well, just to make sure. So this is the little voltage meter on the boards, just to make sure the power distribution's okay. So I shall put that top there. This will tell us if we've got any power issues. Okay, that appears to be okay. So we're just going to power it on and see what the current is. Okay, so it appears to be okay. We've got 4.82 volts, and it's using about 1.47 amps. So that looks to be good. And we've also got the display and video display, so that all seems to be working okay now. So what I'm going to do now is to connect up the adapter board. So here is our adapter and the disk drive, so we're just going to plug the SATA connection in. You can see here it's got standard Molex power supplies here. So what I've done is I've taken an old cable here, chopped off the ends, and I've now put 2 plugs in there, so I can plug those into my power output there to power the drive and the adapter. Now for the moment I'm just going to rest this. I think we'll just move that a little. Move that out of the way. So just going to place the disk drive over here, and we'll hook up the cable as well, and then this power lead will come over here. So I'm just going to do that, and I'll turn the power off first. So I've just got a little distribution box for doing the power supply over here. Now we just need to plug in that to the adapter's power cable. Okay. And finally, just need to make sure ID cable. So we're actually going to plug in this bit of the cable so we can see there's a key there. And if we look at this, the key is on the lower side here as well. So this should, let me just put this on the other side. Fiddly. So the key is on the lower side. Quite a snug fit. Okay. Just rest the hard drive down there. We'll rest down there, just off to the side there. Okay. So now we're ready to power it on. What I have had to do is increase the maximum current that my bench power supply is able to supply. It was at 2 amps, but when the drive spins up, you remember it was about 1.7 amps when I had the other board plugged in. Now when I plug things in, it actually goes up to about 2.3 amps before settling at about 1.7, 1.8 amps. So just be aware that if you're ever doing this with an IDE drive, you are going to need to provide quite a bit of extra power as the drive spins up. Okay, so that all seems to be running okay. So what I'm going to do now is to show you the software, and we'll have a go at running it. Okay, so I included some documentation from the draft ATA IDE spec, and also some information from some of the other projects that I've used and referenced in this. This is a C program making use of some of the existing Nanocomp routines. And what this basically does is outputs the drive ID information and the first sector from the S-record file from the hard disk. So all we're going to do here is to send down the S-record format of the program down into the Nanocomp. And then we'll also capture the output from the serial port. So we should then be able to see the drive ID information, which I'll explain more about in a later video where I'll talk more in detail about the software and how to program the access to the disk drives. And then we'll also then see the first sector of the S-record file, which will include a lot of the VGA palette information, which is used to populate the VGA palette registers. So we can see here we've got the initial drive information, which will include things like the model number and other drive parameters. And then down here we've got the first SREC file sector. So proving we can actually basically access the drive okay, we'll just save this for later. Now in the next version of the program, what this now does is iterate through all the blocks in the S-record file, reads each sector, decodes it, decodes the S-record file, and then outputs into memory. So this will be putting the VGA palette information at the 4000 range, and then the rest of the DOOM image itself will just be loaded directly into the video RAM. So there's various routines for initializing and accessing a drive, reading the disk data into a buffer, and so this main program does most of the S-record analysis. So I used the structure from the Nanocomp monitor for this. So then finally, it after it's loaded all of the S-record file, it then loads that information into the VGA palette. So we should see that when we first load it, the VGA colors won't be quite right, and then at the end, when the palette's been loaded from the data in the file, we'll see it should look just like the DOOM logo that we had in the earlier videos, where we were looking at the high-res colour. Okay, so we're just going to capture the log from this as well. And when we look at this, we're just going to look at the video capture. So as this is reading the S-Record file off the disk, it's decoding it and writing it to the video RAM, so we're able to see this. And as you can see, the palette information at this point in time has not been loaded from memory into the VGA palette video digital analog converter. So once it's got to the bottom, we'll then see it will flash up with the correct color palette. And you can also see on here we've got snow from the CPU accessing the video RAM at the same time that the video controller is using it. And on the later videos, I'm going to look at how we can hopefully eliminate or at least reduce that interference that we get from accessing the video RAM. So one other thing I should mention, I did need to put some pull-up resistors on the PLD input pins. Was getting a little bit of data corruption, and some of the checksums on the S-Record were failing, and it was only randomly happening on certain data, but by putting the pull-up resistors on there seems to have actually solved it. So now at the bottom here, hopefully the video palette, the digital analog converter palette information will be loaded, and we should get a more recognisable rendition of the Doom startup screen. So there we have it. So that seems to be working quite nicely. It's about the same sort of speed as the serial. I suspect that the C program doing the S-Record is not quite as efficient as the assembly language in the Nanocomp. So I'm just going to look at the output file. So we've got the drive ID information, and we can see here that we've got all of the sectors as they're being read. And finally down the bottom it will be detecting that we've got the end of S-Record S9 file and then loading into the video palette. So that's a hard disk interface done. In the next video I'm going to be looking at fixing the snow on the output of the video RAM on the next project phase. I may do a small video about the software. So thanks for watching. If you found it interesting, please hit like and hit subscribe if you don't want to miss future videos.